today. I'm going to be talking about some of the automation that we have been undertaking to address workplace shortages through the pandemic, and then forward-thinking projects that we are working on to address matters related to workforce shortage post-pandemic. I'm glad I see some data science people here. Chris, nice to see you here. Thank you for joining. Chris is a big contributor to data science over at PHSA. So without further ado, these are my disclosures. I sit on the board of directors of the American Association of Clinical Chemistry and of a clinical mass spectrometry meeting. I have some research relationships with SciEx, which is a mass spectrometry company. Today, we're going to be talking about open source tools that we can use for free and that the health authority has embraced. And so it's not a matter of they will install them for you as you need them, and will identify opportunities in the clinical lab space for data science applications, and then understand opportunities in something that is not new, but it's become new to the healthcare industry, which is robotic process automation. And I want to show you some ways in which you can perhaps apply robotic process automation in your workplace to highly repetitive tasks. So what I observe, I mean, below we have somebody who's in healthcare administration, or maybe they're a medical director or an operations manager or director, and they're looking at their processes and they're looking at their staffing shortage, and they usually opt for button one. They usually ask for more budget. But our philosophy is that out of necessity, we are trying to remove inefficiencies. And there are many inefficiencies in healthcare workflows. Those of you involved in ground care, patient management will know that there are lots of workflows that are designed in improvable ways, let's put it that way. And that's not really an indictment. Healthcare is a people-oriented business, and it attracts people-oriented people, and they don't generally have engineering or computer science degrees. And so it's understandable why people focus on the people and not the workflows. But healthcare nowadays needs engineers and people who are focused towards the physical sciences to look for opportunities to improve things. So I'm going to talk about one old story, one story that is mid-cycle, and one story that is we're working on. And so this is a completed story that is still in use, and it relates to the pandemic. And we're going to be talking about what we did for COVID sample pooling. And some of you will know about this, so apologies if you do, but we built upon that stack meaning the computer stack, to add some other processes on, which we'll be discussing later. So in the summer of 2020, there was a worldwide shortage in consumables for reagents for SARS-CoV-2 testing, as you know. And in our case, our fully automated platform was the Roche Cobas 6800, which we thought was going to be our godsend. But by the middle of that summer, we were no longer receiving the reagents. And you can't just retrofit homebrew reagents onto this device. You have to use the reagents that come from the company. And so with the shortage of those reagents, we were faced with having to use more manual methods and try to come up with a way of squeezing more tests out of the kits that we had. And we were getting a ration of kits, and we had another method that was more manual. So because the testing positivity rate was below 5%, we had the opportunity to do this thing called sample pooling, which I'm sure many of you have heard of, and it will make intuitive sense. You just add multiple patient samples together, and if the mix tests negative, then everybody can be reported as negative. And if the mix tests positive, there are various ways to sort out who is positive. You can just test each sample one by one. That's the simplest approach, and that's called Dorfman pooling. Now, if you look at the pooling literature, there were a lot of mathematicians writing papers in the summer of 2020 saying, you know, we've got the mathematical solution to the COVID testing problem. All you need to do is use this highly sophisticated mixing algorithm, and if you run your samples and you put one sample in multiple places on the plate, and you mix in such a way that however the pattern of positives come out, you can impute who is positive and who is negative on the whole plate. Now that sounds like a great idea, but it misses two things. One, Programming the liquid handler is not a simple task. It's its own programming language, and we didn't have a lot of time. The second thing it misses is that, well, there's three things. The second thing it misses is that when the technologists do not understand the process that is occurring on the samples, they are very skeptical of it. And when something goes wrong, they want to be able to troubleshoot it. And if it's very complex or a black box to them, then they're not going to be able to do that. The third thing, and I think this is the most important thing, the more you move the pipette tips over the deck, the more probability you have of contaminating wells with one another. So you want to minimize pipetting activity. So we decided to just go with Dorfman pooling, where we're taking multiple samples and putting them into one well. Now, I've pictured it like this. That's actually not how the liquid handler was doing. It was doing the whole plate once and the whole plate again, and then the whole plate a third time and the whole plate a fourth time. But the principle is there. 4 different patients are going into one pool. Now, the reason you don't often do this in clinical chemistry testing otherwise is because regular clinical testing has linear response, but PCR testing, because it's associated with an amplification process that is exponential in nature, you don't lose much sensitivity when you mix samples together. So it's particularly suitable to this kind of testing. And so we mix the samples together and we test each well, and then we report out the negative wells as negative. But the question, that was begged was, well, when I proposed this, it came upstairs to virology and proposed this, people were like, no, this is a crazy idea, because how are we going to keep track of all this? I said, no. This is going to be easier than what you're doing right now. You are not going to have to think about anything. Everything is going to be taken care of. So Mahdi, who's on the call, and I walked down to Staples at noon and bought a solid state drive and went and poached a computer, an old computer, a throwaway computer from anatomical pathology, installed the hard drive, and started programming immediately after we'd installed Linux. So again, this is not mathematically optimized pooling. This is the simplest kind of pooling we could do, because we had a 4-week timeline from the time of conception to implementation. So we wanted to keep all of the programming workflow as simple as possible. So this is the kind of thing that induces fear in the technologists, which I alluded to earlier. They've read about, this is an idea where if you were pooling 12 samples, for example, and you taking 12 samples and putting them into, or you had a pool of 12 samples and you wanted to, and it was positive, and you wanted to figure out which sample was positive, you could then subsequently break it into 4 pools, and then after that, break those pools down into individual testing. So this kind of thing just makes people shudder. So we kept it simple in that we kept the number low also. So we started with pooling of 4 samples rather than pooling a high number of samples. And there's a reason for that also. When the positivity rate is high, the value you buy by pooling samples together gradually decreases until you're actually penalizing yourself by doing sample pooling. So at that time, the positivity rate was about 1%, but it could fluctuate to 2 or 3%. So we had to decide, based on this figure, how many samples we would pool together in order to get the best bang for our buck when it came to the reagents. So we happened to settle on 4-plex, but we did program the device to do 6-plex, 8-plex, and 10-plex pooling. And so if the positivity rate dropped below 1%, we could flip up to 10-plex pooling and theoretically increase our output by about 8-fold or something like that. But as you can see, because you do have to do tests in singleton on wells that come out positive, you don't get quite the fold change that you would hope in the amount of reagent that you have. So with a 4-plex pool and say a 2% positivity rate, we are buying 3 times as many tests for the one test. And that's more or less where that worked out. So this was the workflow that we had, and we were not using the Roche Cobas 6800. We were using some more manual extraction process on a device called the MP96, followed by thermocycling on the LC480. So from the Hamilton Vantage liquid handler, the samples barcodes were read automatically by the device. and it identified which samples went into which well and concatenated the identifiers together. If the sample happened to cause a problem with clogging of the pipette tip, which did frequently happen because of mucus in the samples, then it would remove that sample from the pooling. And one of the things you are trying to avoid, of course, in these kinds of scenarios is that one of those mucus strands would get dragged out and draw mucus across all the other samples. So you really do want clot detection on to prevent you from doing just that. And then we wrote some software that would convert the output of the Hamilton liquid handler to XML, which is sort of a way of structuring data. And we wrote XML that was compatible with the MP96 to trick it. And so the data would come into the MP96, and then the data would automatically be forwarded over for amplification, keeping track of the barcodes again. And then finally, we had a process to report the negatives out to the lab information system via data innovations. So I want to show you a little bit more about how that, this is just sort of looks like a whole bunch of things, but I'll try to explain what we had cobbled together in the 4 weeks. So we had 3 liquid handlers, and remember, we had no idea how many specimens we were going to be asked to do. The most we ever did was 2,500 in a day, but there were theoretical risks that we could be having to do 3,000 or 4,000 specimens in a day. So we had to be prepared for that. So every liquid handler, we wrote programming to do the batch conversion of XML. We had this pooling server, which we had obtained by this old computer from Anatomical Path. We had also bought a second server, and I'll talk about the replication process for that. And we stored all the code on GitHub. That's not very, GitLab, excuse me, not very surprising. The company, Roche Diagnostics, did not want us directly to interface with their computers because they were running old versions of Windows. So they put a hardware firewall in front of their device, and they also put something called network attached storage. And so what we were doing was all of the file sharing between these devices was going through this network attached storage device, or NAS, which is just a little Linux server. And then our server was communicating with that Linux server to do the data processing for it. And then we had a graphical user interface, which was frankly the hardest thing to write in terms of time consumption. And Mahdi did that. And then the results would go out to the lab system. So how did we do the validation? Well, we started with low tech. We pipetted colored water to make sure that we never got red mixing with yellow or blue mixing with green. And then we would look at the bottom of the well and make sure all the colors were pure as they should be. And then it was on to a higher tech validation where we took samples that were known positive or negative, and we mixed them into mixes. And then we saw how much the cycle threshold was affected to make sure we weren't losing too much sensitivity. And we did lots of plates where we confirmed that we could see and pick up the specimens that were positive. Now, I will say that when you do sample pooling like this, you do occasionally create wells that are falsely positive. You don't create any false positive results because you end up taking that positive well and testing each of those samples individually, but you can get false positives on any given well. So this dashboard was written in a tool called R-Shiny, which is a web app building tool from our studio, which has been recently renamed to Posit, is the name of the company. And so Mahdi developed this dashboard for the technologists to review the results so that they could go out to the lab information system. You can see that the SunQuest container IDs are here, and they are concatenated one to another. And then we have the well position. And when a well is positive, like this well D1, we will get the cycle threshold value here. And when it's time to release those results, all these results from this row will not be released. And then all 4 of these samples in well D1 will need to be tested in singleton. And so when we racked them, we racked all the D1 samples, all 4 of them, in position D1 of a 96 well 8x12 physical rack. And we had to order those special because that's not the standard layout of a sample test tube rack. So when it's time to release the results, we have to break apart those container IDs because we're going to be sending a result for each specimen. And so we just parse those container IDs, and now we are going to release ABC, A1, B1, C1, and there'll be 4 specimens associated with A1, and then we'll all get a negative result. And so we built a little bit of visualization. So for this plate, we had, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 positive wells. That would mean that we would have to do 40 singleton analyses, and all the other wells would be released as negative. Excuse me. And this is how it would look as it went out to the lab information system. We say the device name, the container ID, and then some control results, and then the final result, along with some canned comments that go out with the result. One of them indicating that the sample has been pooled, which is a requirement, a recommendation of the US CDC. So on this particular run, we released 336 records rather than the normal, which would be about 93 records or 92 records that would go out. So we bought ourselves 3.2-fold number of tests, and that was the goal of all of this. So on September the 20th, we went live with this software after a very intense 4 weeks, and it was very much appreciated. And so all of the other tests that we did, including all of our singleton tests, started flowing through this software, except those that were on the Roche Cobas instrument, which had automated communication with the lab system. So to date, well, to about 4 weeks ago, a little further, a few months ago, rather, in June, end of June, we had released 236,000 container IDs. And because many of these tests were multiplexed, that corresponded to about 600,000 transcription events. So 600,000 times that otherwise technologists would be typing NEG or POS into the lab information system. So that was, you can add up how much time that is, but it's a lot of time. And the process, of course, doesn't have the errors associated with it that normal transcription does. Some key points, I did mention that the nasopharyngeal collection tube, we wanted to pipette from the original 16 millimeter by 100 millimeter tube, but the problem was the mucus, and every time we tried to pipette directly, the mucus was a problem. So we did not embark on processes like freezing to break the mucus up, or adding something that would break it up, like a reducing agent. But if I were doing it all again, I would suggest that when the collection is performed, that perhaps you could swirl it and then take the mucus out with the NP swab and throw it in the garbage. I don't know, Linda would comment on whether that's a good or bad idea, but I would have liked that because I'd like to get rid of the mucus. That would be great. We did arrange to be able to do pooling on the 6800 device, but we weren't getting enough reagent for it to matter particularly. And so we never did that, but we could remote into the back of the device, get its XML results file off, and do the pooling from that device. I want to highlight a few tools that we used and explain what they are, because we had to build something that wasn't going to break in the middle of the night. So having one old computer from anatomical pathology was not a good idea. So Matthew came up with this idea that we would have the two devices talking to two devices, both Linux servers, talking to one another, and that we would deploy on something called Docker. So that happened as time went on. So Docker is a way of making it so that you can deploy a small virtual machine without the usual overhead of a virtual machine. And it allows multiple users to use RShiny at the same time. Those familiar with RShiny will know that the company doesn't permit you to have more than one user using your dashboard at once. But if you use Docker, you can have each user getting their own R session and their own Shiny session. And we used something called Shiny Proxy to take care of the authentication on that. That is logging in. And then there's this really great tool called Docker Swarm, which allows the two Docker instances on two separate computers to talk to one another, so that if one computer dies, the other one will come up and maintain the service to the lab. And so we didn't have any downtime except planned downtime in the, I guess we're coming up on, it'll be 3 years or something like that next summer that this has been running, 2.5 so far. But as excited as we were about this achievement, the positivity rate eventually got in the way. And so the positive pool rate was becoming too cumbersome. So about the early November, we were hitting positivity rates around 5 or 10%. And so I was talking to Kennard Tan on the phone, and he said, you know, you can tell which samples are going to be positive based on the postal code that they come from. And I was like, jeepers, that's a good idea. I have the postal codes of the specimens. Why don't I just filter out the patients who come from postal codes that have had a positive in the last 2 weeks? And I picked 2 weeks randomly. I mean, that could be optimized, but, and so I went to Maddie about this about 3 in the afternoon, and somewhere between 3 in the afternoon and 2 in the morning, Maddie completed another app. And the app was an app where you would wand the specimen before you racked it for pooling, and it would tell you whether to pool or not. Now, our charge tech is named Tanya, so we called it Tanya's Little Helper. Many of you will recognize the reference to The Simpsons here. And so if the specimen was from a postal code that was previously positive in the last 2 weeks, it would say, do not pool. It would say singleton. And if it was not, then it would say poolable. And so we were wanding them as we racked them by the next morning. And that actually worked. So you can see that it worked because the pooled positivity rate, pooled sample positivity rate, and the routine sample positivity rate matched one another exactly until November the 6th, when we started to do this postal code diversion. And then the global positivity rate of the lab stayed high, where the pooled sample positivity rate departed. And then we started thinking, well, you know, there's more data in there than just the postal code. Maybe, you know, people who have had lots of tests in the past are likely to have more positives because they're worried. They're getting tested a lot because they're exposed to COVID in their workplace, say, something like that. So we thought, okay, well, this is a good opportunity to look at a machine learner for this. And so we started to explore, is there more than we can do than just the postal code? Unfortunately, the positivity rate got so high so fast that we did discontinue sample pooling in December, but we did pursue this idea of, like, could we predict which samples are going to be positive based on just demographic information that comes with the Sunquest login. And so we tried many machine learners. Of course, we have perfect retrospective data to do this kind of thing, and we can run that model. We could run that model continually to see if the kinds of things that we're predicting positivity changed. And so the easiest one to quickly deploy that was performing well was a random forest model. And in our initial evaluation, we were able to decrease the effective positivity rate of our pooled samples by 50%. So if it was 10% in the global population, we could knock that down to 5%. Now, that wasn't enough for us to pursue it, but this is a machine learner that is very low risk. In fact, no risk to patients. It's operationally an improvement, and we have very good training data for it. So we did want to deploy this, but because the positivity rate after that, you'll remember, was like 20, 25%, there was no sense in trying to do sample pooling. But, you know, for the next pandemic, we'll be ready. Hopefully we'll have a low positivity rate. So when we started, we had many individualized processes. We had paper workflows. We were using USB sticks. I call that sneaker net because you're walking between devices with your USB stick on your sneakers. And we had manual result entry. So people were, and that may be shocking to you researchers, that people were keying in your results by hand, but they were typing NEG and POS all around the province. But by the end of the pandemic, most labs had sorted out an automation procedure. Not dissimilar to what we were doing. And at the end, there was no manual pipetting except that decanting process where the sample was decanted from the original tube with the mucus in it to a secondary tube. We had automated pooling and for both our pooled workflow, automated pooling and automated reporting for both pooled and singleton data workflows. We had networked 10 instruments with 2 Linux servers, 3 if you want to count the network attached storage, and everything was acting as, we had a backup procedure too. So, and we had also set up a MySQL, a Maria database to look up samples that had flowed through our pooling software so that we could, find the file and examine based on container ID as needed. So project number 2 is working, but not deployed. So it's at the research stage, and it is a tool for sample mix-up and dilution detection. And all of you will know who work in clinical lab that from time to time, we do collect the wrong patient and we label it with someone else's label. This is usually detectable by a large and unexpected change in one of the results on that patient, but occasionally is not detected. And very occasionally it can result in giving somebody a diagnosis that they weren't expecting to have. So I have been involved years ago in a case where somebody was told that they had hepatitis C based on a sample mix-up. And of course, that's not a conversation that you want to have when you're trying to explain how that came about. So this has been improved tremendously by Cerner's Clinical Collect, which went live it went live with Cerner for nurses and it went live for lab last November. But believe it or not, sample mix-ups still do occur because none of our outpatient collections go through the Clinical Collect device. So I want to talk about the traditional approach for finding these specimens where the patient collection has been mixed up. Specimens serially collected from a single individual. So if I collect on myself and if I collect on myself tomorrow, most of my blood parameters are going to stay about the same. And if I'm very sick, they might change rapidly. But if I'm stable clinically, then I'm not going to see too much change. And the amount of change that I see is dependent on 2 things. 1, there's the analytical testing performance. And 2, it's the biological variability. That is, how much does my value vary according to my physiology over time? And the greater the time gap between the 2 collections, the greater the difference that we would tolerate. And so those tolerance limits are known. They were explored in the 1970s. And so we have values that estimate the difference we can expect between 2 serial collections on a patient. They are obviously dependent on the concentrations of the analyte in the patient blood, but you have to make rules for the whole population. So if I test my CBC today and I test my CBC tomorrow and I see a big jump in my MCV, my mean cell volume, but there's no reason to explain it, I might posit that I have the wrong patient sample. Now, much more common in the lab and also required to detect is the dilution of a patient sample with saline, and that's very common. Nurses will collect from an arm in which there's an active saline line, and they can contaminate their specimen with saline or whatever happens to be flowing, antibiotics or whatnot. And we get, you can get unexpectedly low results for most things, and then sometimes unexpectedly high for chloride or sodium. And so we want to be able to detect those things too. So delta checking implementation as it exists right now, everywhere where I know that they're doing delta checking, it's single analyte, meaning if I'm collecting 2 CBCs, I'm checking the hemoglobin by itself, the MCV by itself, the platelet count by itself. And if one of those rules is tripped, I consider that a specimen that needs evaluation. I might look and see if I have some evidence that it's the wrong patient, or maybe they got a transfusion, or maybe they had a hemorrhage, for example, or some other interstitial illness that could account for the changes. So this concept hasn't changed since the 1970s, and it's usually built into the middleware. For those of you not familiar, the devices rarely talk directly to the lab information system. Usually there's a piece of software in the middle that will process the data and withhold results that should be held back. So delta checked results do get held back from being reported, and the technologist is flagged that they should have a look at that sample, look in the clinical record and see if there's an explanation. The delta check rules as we have them right now tend to have a high positivity rate, false positivity rate. So many of the delta check flags end up being false positives, and there's nothing wrong with the collection. So here's our current delta check rules for CBCs. We're going to focus on CBCs because that's the data that we flow through this right now. If we see an absolute change in the MCV greater than 5 femtoliters, if we see a platelet count that drops more than 50%, or if we see a hemoglobin change that is greater than 40 grams per liter in a time change less than 3 days, then those are our current delta check rules. And those are pretty standard. They're from the literature. Notice that each of them is applied individually, and there are only 3 of them, even though there are 15 blood components reported in the CBC. So they are statistical in nature, as you might imagine. And so the natural thing we might ask in terms of an opportunity is, could we use all of the results at once to predict whether the entire sample is affected based on multiple analytes? So we would call this a multi-analyte delta check. And we are not the only persons who are thinking about this. I've provided a paper from Yamashita et al. Looking at other more modern statistical approaches to the delta check problem. But we decided to try a machine learner on AWS, as it turns out. And I have to give Matthew Mobini credit for all of this because he did all of the model development on Amazon Web Services. Now, when it comes to machine learning in healthcare, I do just want to make a little plug for something that I am, it's my little soapbox or something I'm concerned about. When it comes to ML in healthcare or AI in healthcare, I think we should choose projects that are likely to make it to the finish line. I would like to see the project to be low risk. So if there's a mistake made, nobody gets hurt. I would like to take care of highly repetitive tasks that are amenable to automation. I would like tasks that are easy for humans to learn, because if it's easy for a human to learn, it will be easy for a machine to learn. Diagnostics, straight diagnostics with a machine learner is fraught with regulatory problems, as you know, because you are making a medical device when you do that. And so deployment is going to be very gray, particularly a black box like a deep learner or something like that. Diagnostic tools that are rules-based, where the rules are transparent, of course, is just de rigueur in lab medicine. It happens all the time. So I feel like decision support is kind of a better area of focus. And all of my friends who have built machine learners brought their machine learners to this grave that we call PubMed. Now, meaning they never actually get deployed. AI has a serious last mile problem in healthcare. You build the model, that's actually the easy part. Deploying the model and getting it to talk to the different kinds of software in the system, whether that be Cerner, the lab information system, some kind of order entry software, something in the community, that's a big problem. And people really underestimate the challenge associated with deployment. I think it's actually a bigger problem than building the machine learner, because the tools for machine learning are so comparatively easy to learn than they were when I got started at this sort of 13 years ago. So here's our data model description. We took the CBCs from 5 years of data from St. Paul's and MSJ. They were anonymized, of course, and stripped of all patient identifiers. We built 65 features from them. And you might wonder how 65 features come from 15 results. Well, you can look at the change, the absolute change, the percent change, change trends, the direction of the change. So it's pretty easy to come up with 65 features. Of the models that Matthew tried, XGBoost worked the best because it allows for missing data. It is frequently the case that the CBC device, the Sysmex, is not able to produce one of the results, and you don't want the model to be dependent on every result in the 15-plex panel. You want it to be dependent on some subset. And so XGBoost allows you to have missing data. And then we containerize that model. That is, we put it in one of those Docker things, and we have hosted it on-prem and then also on cloud. And then we built an API, which an API is just sort of like a talking, how to describe it. It just sits there and waits for data to give you an answer. You just send in some CBC data, just the raw data, and it'll send you back, yes, delta check, or no, not delta check. And so it does that service for you. How about the deployment? As I mentioned, we do a lot of these things with our Shiny. We use some other tools that I should mention: I notify wait for watching directories for the appearance of a file, Plumber for building the API. We use PySocket for doing some communications between the device and the machine learner model, and then Docker Swarm again. And I just want to plug something called Kubeflow, which is very nice because, as you know, there's a competition between Amazon Web Services and Microsoft Azure as for whose cloud tools will win in healthcare. And Kubeflow is a way of deploying that is agnostic to which vendor you're using. So however we build it, we can deploy it in any of the above. We built on top of the architecture that we had constructed for pooling. So we've got the hematology analyzer talking to our servers, either on-prem or in cloud. And when it comes time to deploy, the results from the machine learning model can be requested from Data Innovations, the middleware, and returned to Data Innovations so that it could make the adjudication, please hold this result back or not. But in the intervening period during the study period, what we will do is just have a dashboard showing the results of the machine learner and indicating whether the specimen ought to be investigated. How about performance? Well, we have been able to get a performance that is about 15% higher in F1 score. That is, if the current rules are coming in at, say, 73% sensitivity, this machine learning is coming in at 96% sensitivity. You might wonder, how did we train it? Because we don't have that many real delta checks in the past. We took the raw data that was anonymized and we made deliberate record swaps so that we could create artificial specimen mix-ups on the same floor. So we took 2 records from floor 7 that were collected around the same time that could have been, contemporaneous and collected by the same person, and we just swapped them. And so we swapped at multiple levels of positivity for a delta check, 1%, 0.5%, 0.1%, and up to 20%. And then we trained all those models and see how they perform. So like many machine learning models, it looks amazing in theory. And so when you go into practice, you want to see what it's actually doing. So in real time, we can now see which specimens it's identifying as potential delta checks. Now, nobody's having to do any work about this. We won't want to affect operations until we're sure we're making their lives better. But we can monitor which specimens would get flagged. And in the blue is the XGBoost model. It's identified 138 specimens in the trial period that was not detected by the current rules. The current rules detected 417 that were not detected by XGBoost, and there was a common pool of 126. So the natural thing to do is to go and see, well, what are these 138 specimens? What's really happening? And what's in this 126 also? So MACD built a little dashboard for us to do exploration of those. And it is finding dilutions, and it's finding people who have rapid changes in their health status, if they sort of rapid development of liver failure or rapid development of renal failure. That's not surprising. And then what we are now building on is the ability to detect those dilutions also. And we have a large catalog of real dilutions that we found for sure that we can check against the model. So this is, what would I call this? It's deployed for research purposes at the present time. And so we're pretty happy with an automated data workflow from the device to the machine learner. Project 3 is in its infancy, but I want to bring an idea to you that you might be able to apply in your workplace. So what is RPA? RPA stands for Robotic Process Automation, and it's a way that a computer can interact with another computer. A piece of software, rather, can interact with a piece of software. So let's say that you work for Ticketmaster and you have no way to get data into a database except by manually keying it in, but you have it in an Excel file. You can write software that will read the Excel file and move the mouse on screen and enter your data for you. That's a typical kind of commercial application, and it's very big in use in companies and businesses. But we can apply that to low risk tools in low risk scenarios in healthcare, and we could have it monitored by a human to make sure that it is not making a mistake. And as you know, we have to do a lot of manual entry at the login process for requisitions in radiology, for requisitions in pathology and lab medicine. So old school RPA was something called TCL, and that came out in the 70s. And then in the 90s came something called auto hotkey, which was developed for gamers who didn't want to put, who wanted one keystroke to do a series of keyboard strokes that they would use in their games. And then that became something that people would use in a kind of more commercial level. And then there's some browser specific ones, Selenium, which has bindings for R and Python. That is, you can interact with Selenium through R and Python. UI Vision is probably the market leader. But I do want to mention one that's that the Health Authority has in its arsenal, and that is Microsoft Power Automate. Microsoft Power Automate is like RPA for everybody. And you don't have to have a computer programming mindset to use it. You can just do it the same way you build macros in Excel. So if you can build macros in Excel, you can use Microsoft Power Automate, but you can do a lot more things with it than macros in Excel. So it comes shipped with Microsoft 11, just like many other core Microsoft tools. So do have a look on your Microsoft 11 or Windows 11. You will have Microsoft Power Automate. And it is sort of like after one day of use, you can do some pretty interesting and neat things. And if you spend a few months at it, you could really amaze people. So what can it do? Well, it can do optical character recognition built in. It can read barcodes. It can recognize images on screen. So if you have a process where you always have to click on the cat, it will be able to see the cat and click on the cat. Now, it has to be the same cat each time, just warning. It can launch other scripts. So it could launch a script in your favorite scripting language, whatever that happened to be. It could perform a SQL query for you. It could move files around. It could move between different applications. Maybe you have to interact with Sunquest and Cerner, or you have to work with, two different applications that are both on screen. It can raise the focus of one and bring it to the other. So any kind of highly repetitive manual process can be automated. So why do we care? Well, we've lost a lot of our workforce from the pandemic. And some of the labs are having trouble maintaining their workforce and have many open positions because they're in a more expensive area of town. So this delays sample registration, which slows care. And you wouldn't know this, but I will tell you that the Ministry of Health has noted a disproportionate increase in outpatient testing over and above the usual rises. And this is attributable to the remote visits that patients are having with their physicians. So there's a big lift that's been pushed against outpatient labs. And we did have a temporary increase in our workforce associated with COVID, but that is coming to a close. So that's why I care. Now, this isn't RPA, but it's what we did first. We wrote some software. I'm sure many of you know Horatio Bach in the Department of Microbiology. He's a friend of pathology and lab medicine. Well, his son is Evyatar Bach, and Evyatar is a computer physicist. And when he was in high school, he was just a very keen young man. And so he wrote software for us in the summer to scan our outpatient requisitions, find the barcodes, and save the contents, the PDFs in folders according to today's date on our shared network. And so when you want to find a patient's requisition, whether that being a standing order or what have you, you can just go Control F, search for the PHN, and all the requisitions of that patient will come up. So that's been in production since January 2013 without a hiccup, and we're very thankful for his efforts that summer. But we might ask ourselves, can we do more? Because with Microsoft Power Automate, we could pull out all of the patient information. If it was typed with the OCR, we could pull out the patient information that is in the barcodes. We could look at the EMPI table provincially. EMPI table is like the healthcare registration table. By my PHN, I find my name, full name, my birthday, my address, my telephone number, and all that stuff. All that stuff that is registered the same everywhere in the different health authorities. So we can query the EMPI table and pull the patient information down, or if we could see whether the patient is not in the EMPI table and extract that information from the piece of paper. And Matthew had already written something like that for the home run antigen testing. You remember that people could go home with a kit with antigen tests in them and they could test themselves, and CDC would wanted to have the data on that, but there was no way for this little point of care device to pass that data to the lab system. And so the home kit tool would permit the user to scan their care card and provide information to the lab techs, and then the Microsoft Power Automate would be able to enter that into Cerner through the Citrix instance on that person's computer. So that had already been trialed. It didn't go into production, but it certainly was available for use, and the performance had been noted. So here's an example of how we can use Power Automate to improve workflows in the clinical laboratory. This is a nice example of an outpatient laboratory requisition that we have received from another institution. Now what you can see is that we have very clean text and we have barcodes. Now there are barcodes hidden because they contain patient information, but there's a barcode for the PHN, the birthday, gender information, the address, and the accessioning information from the other institution. And even if that weren't there, we have very clean text that we can perform optical character recognition on. And most importantly, the test that is requested, in this case alpha-1 antitrypsin, is typed very neatly at the bottom, and we can take that code A1AT and map it to whatever code we're using internally. It happens to be the same, but it's not always the same. And so this is not an original requisition. This is a requisition that has been processed by Interior Health, and they have done all this typing already. Now, many outpatient requisitions don't have nice, clean information like this, but as you can see, we could scan this image and quickly extract all of the relevant demographic information that we would need for any kind of registration process for the patient's sample. So how do we decode those barcodes? Well, there's a few open source barcode libraries that we've been using. ZBAR is the one we use the most, but I use the Data Matrix barcode library for LifeLabs requisitions, and many people use the Zebra Crossing barcode library, which I have not tried yet personally, but I'm sure it's not much different. Now, here's an example of maybe a third of our requisitions are like this. So they're handwritten, and this is just extracted text from the bottom. You can see that the requested test is HCV. That's not something we're going to be able to deal with. So what are we going to do with these handwritten requisitions? Well, you scan the requisition, you try to extract information. If you are unsuccessful, you can move that file to a folder that for human processing later. So we're not going to be able to do everything this way. We're just going to be able to do a portion of it. So how does the workflow go in this proposed process? Well, we would scan the requisition on the scanner. The image comes in. The barcodes are identified by the barcode library. Failing the extraction of the information from the barcode library, you would then perform OCR and extract any information that you could. PHN would be the thing that you would be looking for. You would launch Cerner. If you've extracted the PHN, you can check it with this Mod 11 formula to make sure that it is not just a 10-digit number starting with a 9, but it is actually a PHN. Then you can look on the provincial registration database from your terminal to see if the patient is registered there. Well, actually, you would check whether they're registered in Cerner first, and if they're not registered in Cerner, you would pull their data down from EMPI, and failing that, you could do the registration manually. But hopefully, you can get all of the registration information from the EMPI database and then move that over into Cerner. They might already be registered in Cerner, so that process might not be necessary. So you can imagine there's a lot of if-thens in the workflow, but that's something that you can do conditional things without any trouble in these RPA programs. One thing I would point out is that a little harder to deal with the standard outpatient lab requisition because the text is so tiny and the tick boxes are tiny. There are ways to detect, of course, whether a tick box is ticked or not. But I don't anticipate us being able to manage the standard outpatient lab requisition, mostly the requisitions that are coming in that have been processed somewhere else and are nice and clean. In any case, once that whole process of getting data into Cerner as needed and into Sunquest as needed is complete, then you can have it print the barcode label for the sample out, and then you can label the samples accordingly. That would be the manual part of the process. So with that, I will stop. I would like to thank a few people who have been critical in all of this. Grace Vandergugten programmed all the liquid handling for the pooling project. Mahdi Mobini, who's come up a few times, did all the graphical user interfaces and done a lot of the back end programming, particularly on the Delta Check project. So thank you to Mahdi. And of course, all of the medical and technical staff at St. Paul's Hospital and Roche Diagnostics were very helpful when we were under that time crunch in September of 2020. And with that, I will stop. If you have any questions, please don't hesitate to contact me, and thank you very much for your attention.